All right, welcome back. Another day, another dollar. We have homework 2. Goal is wrap up any loose ends and answer questions today, and then Friday be able to work on project number 2, so module 2 project. Where do you want to get started? What are you looking at? Done? There's 24 hours left. How could we be done? Just getting started. The old college effort. Take a 6-week project, do it in 26 hours. Yeah.
Can you go over 1.3 part 2?
1.3 part 2. Which prediction?
It is 1.3 problem 2.
And sorry, what was the?
It talks about semiconductors.
So like part 3, and then trying to find like best fit line for Moore's law.
Yeah.
This Gordon Moore prediction part. Yeah. Where are we? All right, so let's say my X data points are gonna be those dates of introduction, and might as well turn them into like some values, right? MOS transistor count, and we'll turn that into values. All right, so on a log scale, if I squint hard enough and ignore some stuff, it looks like a straight line. So my goal is, what is that straight line? Like if I'm drawing a straight line through this data, what's the best line that I can draw? And then I'm trying to compare that to the idea that it doubles every 2 years, because not all of these are doubling every 2 years. Something happened in the 90s where it was dropping, and then for the last 25 years, almost every year it doubles, or every other year it doubles. And I could even like try that out. I'm like, all right, well, plt dot semi law. Well, So I want to find, let's do a polyfit of xi and yi. So if I just take the year and the transistor, I get a slope of 1.7 or 0.17 billion. What do we think? Is this going to be good? Is this a good fit? Call it my fit. And I end up with my straight line fit looks like this. Did anyone get a curve that kind of looks like that? Or not yet? It doesn't look like a straight line, right? Something's weird. So go back to, let's look at just the data. Because here I was plotting semi-log stuff. If I put it back onto a linear scale, which is what I was doing the best fit line, that red line, my best fit, it's not a good fit for this data, but it does look like it's the best worst straight line to go through that data. So that's really what I'm looking at whenever I just say like polyfit this year and semiconductor data. So instead I need some kind of log scale, like something to the power of x, like something to that year power. One way to do this, since I'm looking at like doubling, if I put it on a log base 2 scale, then my slope is telling me how many years it takes to double, because 2 to the 1 is a double, 2 to the 2 is a quadruple. So what I could do is say log 2 of yi, and let's put this one back onto semi-log y. Then I still have this weird result that when I took the log base 2, now my predictions are always like 1,000 to 10,000 times less than the result. And that's because I haven't put them back into the normal scale. So I put them on a log scale, did a linear fit. Now I have to put them back into like linear fitting scale. So the last step is I want to say not just polyval, not just taking that function and plugging it back in, but I want to take whatever log scale I use, whether this is log and this is exponent, or log 10 and 10 to that, but something, whatever log scale I took it into, I want to get it out of log scale. So that now I have like on that log, on this semi-log y, it is a straight line because I took the log, did a fit, then took the power to bring it back into log space. And sure enough, the slope here is 0.493, which means that every 1.9 something years, it's doubling, because 2 to the 1, in order for that slope, here, let's say bracket 0 over 2, oh right, sorry, 2 times. So every 2 years, I had like a 98.5% increase in transistor numbers. And meanwhile, Moore's law was that every 2 years, it's 100%. So I'm like slightly, probably the 90s. The 90s did all sorts of stuff to people, but maybe that was like bringing my slope down just enough that we couldn't follow Moore's law. Cool. That was a good place to start. What's it, 1 over that? Yeah, every 2.03 years. So 2 years and what is 0.03? Every 2 years and 11 days. Or 10 days. I don't know, depends on how accurate you want to get. Yeah, 10.6 days. A little over a week. More, always wrong that more. It's off by a week every time. What else are we working on? Yeah. Like the next part, or yeah. Down here, like do some Monte Carlo buckling analysis. Okay. What do we have so far for it? Less? Not too much? Okay. Well, let's start off with what we know. We know we're gonna build something that has 100 steel rods, or yeah, steel rods, 200 gigapascal modulus, and we're gonna say modulus is just constant. Length is gonna be defined by us, just 5 meters, or whatever the length is. We can change the length. We can make it as tall as we want or as short as we want. The taller it gets, the more likely this thing is gonna buckle and fall. The shorter it gets, the more over-designed it is. So I'm gonna set up my Monte Carlo. I like to have these like default values in here like this, so that if I enter nothing, it gives me whatever I started with. And then I'm gonna take this, scroll up a little bit. Oh my god, too far. I'm gonna take this equation and put it right inside my doc string so that I can copy the equation right in here. And I already did this, but I'm just showing you. And let's start from scratch. Oh yeah, let's do this so that we have all the same stuff. From numpy.random import default RNG. You don't need to give it anything. I usually say 42, but we'll give it nothing because we're gonna run it a few times. It just sets a seed, so we don't have like truly random numbers from a computer, but they look random. They look random enough. You just can't use like a default RNG generator like this to like create passwords or blockchain tokens or anything like that, because they're pseudo random. They are predictable. There's only so many ways that they get rearranged. All right, so now I've got RNG, and I can ask for like a normal distribution. The location is going to be my mean value. The scale is going to be my standard deviation. And then the size, I think it's size, yeah, equals the N, like the total number of rods that I want to simulate. Now my buckling load, I'm not going to use like a random number to generate the load, that critical buckling load. I want to use the random R's to calculate what all those random buckling loads are. So I'll say np.pi, this is why I copied it down so I'm not scrolling back and forth, times E times R to the fourth over 16 over L squared. My mean buckling load is critical load mean, and my standard deviation is going to be P critical standard deviation. So now I've got, based on normally distributed radii, so they're coming off the assembly line, they're not all the same radius, so I'm going to factor that into my buckling analysis and try to figure out how tall can I make this thing. Let's do this. Monte Carlo. And if I just open close, it's going to give me the default values. So somehow, depending on what random radii I get, somewhere around 170 plus or minus 60 newtons. And the number that I'm comparing this to is that 1,000 kilogram structure. So I have 1,000 kilograms held up by 100 red steel rods. So that means the total load per rod is like 98.1. So each rod is holding 98.1 newtons. So I want my critical buckling load to be less than 98.1. Or sorry, more than, oh my God, more than 98.1. Because that means that when it's holding that structure, it does not fail. And I've got like some normal distribution of radii that are all transforming into some kind of distribution of critical buckling loads. So right now, this average value is 170 for a 5 meter, for every rod is 5 meters, and then the tails are kind of described by that standard deviation. And we can even like take a look at P critical. If I just add another output saying like, hey, what is this P critical? What are the results here? Oh yeah, we should redefine it, right? And now I can look at like for all those 100 rods, how many of them would fail at a given load. So between like 45 and 55, there'd be like 5 rods failing. Between whatever, this somewhere around here, most of the rods would fail. Some above like 120, something like that. And if I want to make if I want to make this look smoother, then with Monte Carlo, numbers are your friend. Like, just keep increasing n. So right now we had 100. Let's do it 1,000 times. So now we'll have 1,000 different sets of 100. And since we have so many, we can increase our bin size or decrease bin size. Let's do 100 bins. Now I start to see, like, again, if I squint and look at it, it kind of looks like a normal distribution. Really, it's skewed right. Skewed right. I always mix that up. It's a skewed right, yeah. But there, it's not like symmetric, right? There's something off about it, kind of like leaning one way. So when it leans left, it's skewed right, because the mean is further to the right than the mode. And I can even look at, like, how many, look at a histogram of just the stuff that was less than 98.1, like a histogram there. Or I could just ask, like, all right, well, how many? So of that 100,000, of that 100,000 I had with a 5-meter length, like 5-meter tall structure, I have 13.9% failing. So not great. That's not my 2.5%. That's not what I want yet. So what do you think? How do we get to 2.5%? Here, I'll take this. How do I get that number to 2.5?
Yeah.
Yes. Thanks for joining. Alright, just to wrap this up, we never got back to it, but if I start reducing L, change it down to like 4, then I can start seeing lower numbers changing. So if you are checking back in, trying to get to the right numbers, maybe like 4.3. Now I've got, oh, too much, too big. 4.1, 2.7, so it's somewhere around 4, at least based on this. Yeah, based on this analysis with these random numbers, somewhere in there. Cool. All right, thanks.